So new lecture is about spread spectrum. So what is spread spectrum? So it is a transmission technique in which a pseudo noise code independent of the information data is employed as a modulation waveform to spread the signal energy over a bandwidth much greater than the signal information bandwidth. So till now we have seen that we are modulating our information signal through a carrier. That means we are changing some characteristics of the carrier signal, either in amplitude, phase, frequency, that we call like frequency, uh, frequency modulation, amplitude modulation, phase modulation, like PSK, and both amplitude and phase modulation, that is like quadrature amplitude modulation. So that means we are changing something of the carrier to transmit our information. But for that, we need something that we keep our information either in phase or in amplitude of the carrier. So if there is carrier, there must be some frequency. So we have to keep uh, users different, distinct from each other, either in frequency or in time. Then we have this frequency driven multiplexes or time driven multiplexes. So, however, in 3G, we have WCDMA, that is code driven multiplexes. That means we just separate users in code rather than in time and frequency. So that is your CDMA is kind of your spread spectrum technique where we use a pseudo noise code independent of the information data, and we modulate that pseudo noise code to transmit our information. And the main purpose of doing it is to spread our information over a much wider bandwidth than to that of the signal information bandwidth. So that is again a difference from the other uh, modulation waveforms that we have seen in like TDMA, FDMA. So at the receiver, the signal is de-sprayed using a synchronized replica of the pseudo noise code. So same pseudo noise code will be used at the receiver to de-spread the signal. So in spread spectrum, we combine signals from different sources to fit into a larger bandwidth, but our goals are to prevent eavesdropping and jamming. So the security is the main concern of this technique, this uh, technology. You can say that it's try to avoid eavesdropping and jamming, and it succeeded in that. To achieve these goals, spread spectrum techniques are add redundancy, hide a signal below the noise flow, and resistance to narrowband jamming and interference. So it's like if we spread the narrowband energy into a wider band energy. So the energy will spread over a wider bandwidth than compared to the narrow bandwidth. So the energy level will reduce and it will hide below the noise floor because your uh, spread spectrum signal basically a pseudo noise code spread much over larger bandwidth. So its noise floor will be on top of the this narrow band signal that you are trying to send over this pseudo noise code. So resistance to narrow band jamming and interference can be achieved through spread spectrum. And we also can mitigate performance degradation due to intersymbol and narrowband interference. In conjunction to this, we also have rack receivers with a spread spectrum that can provide coherent combining of different multipath components. So rack receivers is kind of uh, the name as you see the racks. So you might have seen a table where you will find different racks, or in the kitchen we have different racks. So they are one, two, three, four, five, maybe more than that racks. So here we have rack receiver, that means which has like 4 5 fingers to receive the signal. Different fingers are set to accommodate different multi-path delay of that signal. One may be with zero delay, maybe one with the full time scale delay, one time period delay, another maybe half time period delay likewise. So they will be received by different fingers of the rack receiver based on their delay, and their delay will be removed and then they will be added. So after that, removing of that multi-path fading, their addition will be the in phase, that we say the constructive addition, that will also help us uh, recovering the signal properly. So allow multiple users to share the same signal bandwidth, and wide bandwidth of spread spectrum signals is useful for location and timing acquisition. So there you can see spreading, before spreading you can see the signal is energy, high energy signal. So this energy of the signal may be spreaded. Maybe this energy comes under this noise flow. So that is quite possible if the spreading is too much. Classification of spread spectrum signals. We have averaging systems. We also have the avoidance systems. These are the two types of spread spectrum. Averaging systems are those where interference is averaged over a large time interval, whereas avoiding systems transmitted signal is made to avoid the interference a large fraction of time, that is interference minus one. And averaging systems are types of direct sequence modulation or PN modulation. It can be hybrid methods, whereas avoidance systems are the frequency hopping, time hopping, and creep modulation. So spreading methods, first is frequency hopping, as the name suggests, uh, where the signal may be transmitted using different frequencies. The bandwidth spreading is achieved by hopping the carrier frequency over a large set of frequencies, and that is applied in GSM, military, ISM bands, and in Bluetooth. Whereas time hopping, a block of bits is compressed and transmitted intermittently in one or more time slots within a frame that consists of a large number of time slots. And in direct sequence, the spreading is achieved by multiplying the data waveform with a pseudo random signal. And that applied in IS 95, 96, 136, cellular CDMA, GPS, UMTS, WCDMA, and in military. Whereas in multi-carrier CDMA, that can be applied in 4G, that is OFDM, orthogonal frequency driven multiplex, that is a multi-orthogonal type of thing that is used in multi-carrier CDMA, that is used in 4G CDMA, and ultra wideband that's used in radar and short range communications. So properties of a spread spectrum are that it occupies a bandwidth much larger than is needed for the information signal. So we use the excess of bandwidth here. That means we spread the energy of the information signal. And the condition is the signal that we are using for spreading should have much larger bandwidth, so that spread spectrum modulation is done using a spreading code independent of the data in the signal. And the spreading at the receiver is done by correlating the received signal with a synchronized copy of the spreading code. So how this started, history is also included here. Uh, it was first described on paper by an actress and a musician in 1941, named Hedy Lamarr, and pianist George Antheil described a secure radio link to control torpedoes. They also had the US patent. The number is 2.292.37. The technology was not taken seriously at the time by the US. Then Army and others was forgotten this technology until 1980 when it became active. Since then, the technology has become increasingly popular for applications that involve radio links in hostile environments. So basically, this technology was first linked to be better performing transmission using radio links, but in hostile environments. Maybe a war environment like. So the typical applications for resulting short-range data transceivers include satellite positioning systems, 3G mobile telecommunications, WLAN, that is your Wi-Fi, and Bluetooth. These techniques also aid in the endless race between communication needs and radio frequency available situation where the radio spectrum is limited and is therefore an expensive resource. Then we have this theoretical justification for spread spectrum. Spread spectrum is apparent in the Shannon and Hawley channel capacity theorem. So Shannon Hartley channel capacity theorem is where capacity is equal to bandwidth log of 2 1 plus signal to noise ratio. So one assumes that capacity, which represents the amount of information allowed by the communication channel. So amount, that means how many bits we can transmit in 1 second, that is your capacity. So that capacity, how much that capacity is allowed by the communication channel, also represents the desired performance, that is signal to noise ratio, and channel is your bandwidth. So bandwidth is the price that to be paid. So whenever you purchase something, you have to pay your money. So here, if we want to achieve some capacity, we have to purchase the bandwidth, or we have to pay the price of the bandwidth. Because frequency is a limited resource, so that bandwidth is not cheap, it's expensive resource and a rare resource at the same time. The signal to noise ratio expresses the environmental conditions. So SN there to express the hostile environment if there is any. In that condition, signal to noise ratio will be low, maybe less than 1. If noise is dominant, maybe we have good channel conditions. In that case, noise will be smaller compared to signal, then the ratio can be greater than 1. So SN determines the conditions of the channel, or characterizes it that its obstacles, presence of jammers and interference. So whatever in the channel that will be characterized by this signal to noise ratio. So there is an elegant interpretation of this question applicable for difficult environments. So difficult environments means we have low signal to noise ratio, and that is caused by noise and interference. So see, so signal to noise ratio become low. Even then, one can maintain or even increase communication performance, that is high capacity. We still can transmit many bits per second. by allowing or injecting more bandwidth. That means if you increase the bandwidth, where your signal to noise ratio is low due to the difficult environment, even when signal power is below the noise floor. Means even in the noise conditions where your signal is below the noise floor, even then you can transmit more bits per second, but by injecting more bandwidth. So this thing motivates or proves that we can transmit a signal hidden by the noise, and even then we can achieve the high capacity. So this that is a modification of equation 1 by changing the log base 2 to E, the Napier number, and by not noting that log E, therefore C over 2, C over B, 1 over log 2 into log 1 plus Sn is equal to 1.443 into log 1 plus S over N. Applying the Maclaurin series development for, so that will be C over B 1.443 into signal to noise ratio, then the series, Maclaurin series. So the signal to noise ratio is usually low for a spread spectrum application, as just mentioned. The signal power density can even below the noise level, assuming a noise level such that signal to noise ratio is less than 1, then the Shannon's expression becomes simply C over B greater than 1.433 into signal to noise ratio, as we exclude the other factors, that is minus 1 over 2 signal to noise ratio square. So if its signal to noise ratio is less than 1, then a square of that will be much less than 1, then we have cube, and then we so on. So we can exclude all the factors of square and cube. We can only keep the original signal to noise ratio. So this equation can be that capacity to bandwidth ratio can be greater than 1.433 into signal to noise ratio. So very roughly you can manipulate the equation. So this will be the noise to signal and is greater than bandwidth to capacity. To send error-free information for a given noise to signal ratio in the channel, therefore, one need only to perform the fundamental spread spectrum signal spreading operation, increase the transmitted bandwidth. That principle seems simple and evident. Nonetheless, implementation is complex, mainly because spreading the baseband by a factor that can be several orders of magnitude forces the electronics to act and react accordingly, which in turn makes the spreading and de-spreading operations necessary. So bandwidth effects of spreading operation, as you can see, we have the baseband signal data in, that is before spreading and modulation. After spreading and modulation, your energy will be spreaded, spread spectrum code and data in BB baseband signal into processing gain, and that is multiply with some wideband signal. So here a spread spectrum demodulation has been made on top of the normal demodulation operations. One can also demonstrate that signals such as an interferer or jammer added during the transmission will be spread during the de-spreading operation. So waste of bandwidth due to spreading is offset by multiple users. So we can allow multiple users to use the same bandwidth and frequency by allocating them different PN sequences. So it's an anti-jamming technology. So Gaussian noise by definition has infinite power spread uniformly over all frequencies for a typical narrowband signal. This means that only the noise is the signal bandwidth can degrade performance. For signals of bandwidth W and duration T, the number of signaling dimensions can be shown to approximately 2 WT. Again, white Gaussian noise with infinite power, the use of spreading offers no performance improvement. So we cannot improve Gaussian noise even we have this spreading. However, when the noise originates from a jammer with fixed finite power and with uncertainty as to where is the signal space the signal coordinates are located, the jammer's choice are limited to the following. So jam all these spectrum with an equal amount of power in each one, with the result that little power is available in each coordinate. Jam a few signal coordinates with increased power in each of the jammer coordinates, uh, or more generally jam all the coordinates with various amounts of each. So figure 12.1, effect of a spectrum spreading, the presence of white noise, spectrum spreading in the presence of an intentional jammer. So A, you can see spreading in presence of white noise doesn't affect it, whereas in the presence of intentional jammer, some of the information may be lost, but still we have some part of the information that is able to be received properly. So jamming is not always the result of an intentional act. Sometimes jamming is caused by natural phenomena. Sometimes it is the result of self-interference caused by multipath, in which delayed versions of the signal interfere with direct path signal. So that we can also mitigate, or we can improve on by using the REC receiver that we have seen, and that spread spectrum receivers are the REC receivers that try to remove this multi-path delay using the different RECs of the receiver. So resistance to interception. So spread spectrum signals are hard to intercept, means no one else can intercept the information in the transmitted spread spectrum signal. So they have the internal or built-in resistance to interception. How? Let's see. That is the second advantage provided by the spread spectrum techniques in this era where we live in a world that where we share our information online, we keep our information on different social websites. We always transmit, we tend to transmit our personal information. So where there are some interceptors try to read our personal information, spread spectrum is a good technology, that's a good technique that keep our data uh, protected, and it has a built-in resistance to this interception. So this is a second advantage, but I will say it's a main advantage of spread spectrum techniques. Without the right key, the spread spectrum signal appears as noise or as an interferer. So the key that is used at the transmitter side, that is a pseudo noise code or sequence used to spread the information. Same sequence can be used to de-spread the information or can decode the information. Without that right key, the spread spectrum signal appears as a noise to the interceptor or as an interferer. So scanning methods can break the code, however, if the key is short. Even better, signal levels can be below the noise floor because the spreading operation reduces the spectral density. That is, total energy is the same, but it is widely spread in frequency. Spectral density means how much power uh, is being provided in a certain frequency. So spectral density is hertz per watt. How much power is transmitted per hertz. So when we spread a signal, this spectral density is spread. That means now we have less energy of less power per hertz. So the message is thus made invisible, and a effect that is particularly strong with the direct sequence spread spectrum technique. cannot see the transmission. They only register a slight increase in the overall noise level. It also has a resistance to fading. Wireless channels often include multi-path propagation, which are caused by atmospheric reflection or refraction and by reflection from the ground or from objects such as buildings. So the reflection path can interfere with the direct path in a phenomena called fading. Because the despreading process synchronized signal D, signal R is rejected even though it contains the same key. Methods are available to use the reflected path signal by despreading them and adding the extracted results to the main one. So that is through the rec receiver. We will remove this multi-path delay in the reflected signal uh, by receiving it through a finger of the rec receiver. That finger may be adjusted to this delay and will remove it and can be not then this R that is the reflected signal can be added into the direct signal. So ranging in of spread spectrum can be determined by comparing the sending time of a pulse and the return time of its echo, and the uncertainty in the delay measurements is inversely proportional to the bandwidth of the signal pulse. Since spread spectrum signals occupy a large bandwidth, the range can be measured more precisely. Again, they can be used in radars due to this uh, property. So, and spread spectrum signal consisting of the range measurement, a long sequence of pulses same, and the echoed sequence is correlated with the local replica to know that the results of the correlation are used to perform an accurate time delay or range measurements. Principles of spread spectrum block diagrams that you can see, we have the transmitter, uh, the data, DT, carrier modulation and amplification, and then we have filtering amplification, and then we have the waveform demodulator. So that is a typical digital communication system. Whereas if you include the spread spectrum, you will add the pseudo noise generator. That will be multiplied with the data signal DT. C of T is your code that is used to spread the signal. Other things will remain the same. Before receiving, we despread the signal before the demodulation at the receiver. So DSS, that says direct sequence spread spectrum. So in DSS, each bit represented by multiple bits using spreading code. Spreading code spreads signal across wider frequency band in proportion to number of bits used. 10-bit spreading code spreads signal across 10 times bandwidth of 1 bit. One method, combine input with spreading code using XOR. Input bit 1 inverse spreading code bit. Input 0 bit does not alter spreading code bit and data rate equal to the original spreading code. Performance similar to frequency hopping spread spectrum. User data stream is multiplied via high rate fast code sequence. Example is here. We have 3 bits. Spreading factor is 7. That means each bit will be represented by 7 bits. Another example, we have data input A, locally generated PN bit stream, and that is multiplied with that, and the transmitted signal is C. That is data input A into the XOR operation is there, performed there with the locally generated PN bit stream. As the receiver receive signal again multiplied with the locally generated PN bit stream. That is identical to the use as the transmitter, and then the data output received as A, that should be same as that was data input A. So that is kind of block diagram of direct sequence spread spectrum transmitter, binary data modulated through BPSK, then multiply with the pseudo noise bit source, and then a spread spectrum signal transmitted. So that is the transmitter. So this multiplication can be done after the modulation or can be done before the modulation. So sorry, that is receiver that despread the data, then demodulate the BPSK, and then we receive the data. So this is another example that says spread spectrum sequence using BPSK example. Data inputs modulated, then multiplied with the spreading code, and then transmitted as a signal D. And D, when we despread, we should receive the same signal as the data in. Binary data with symbol read RS is equal to 1 over TS, that is bit rate of RB for BPSK pseudo noise code with chip rate RC over 1 TC and integer of RS. So basic principle of DSS, that is spreading. In the transmitter, the binary data is directly multiplied with the PN code C of T, which is independent of binary data to produce the transmitted baseband signal. Despreading in the receiver, the received signal RXT is multiplied with the same sequence CRT. So the two sequences are the same. When we do that, we receive our data as shown in the equations. So I stop here on slide 30. We will continue from this slide in next class. If you have any question, you can ask.
Sir?
Yes.
सर वो पेपर के बारे में कुछ बताइए.
जी data. G58.
सर वो पेपर जी कुछ आउटलाइन बताए वहाँ.